Hello everyone, my name is Aaron Standard. We're going to cover something a little fun today, which is the TurboMqtt library. This is a library that I personally developed over the past several weeks. It is currently the fastest .NET MQTT client by a pretty significant margin. It's built using Akka.NET and Akka.Streams. We're going to spend some time in this video talking about why we built this, how we built it in order to make it fast, and what some of our future plans are for it. If you want to install TurboMqtt, it is available on NuGet. And if you click on the link in the description, you can go to the source code and make sure you click watch on the GitHub repository so you can get notified about any updates we make to it. We're planning on adding support for a number of new features in the future. You should definitely stay tuned if you're interested in all things MQTT. Speaking of which, what is MQTT? MQTT stands for the Message Queue Telemetry Transport. This is from the same standards body, this OASIS group. This is also the same standards body behind EMQP, which is responsible for things like ActiveMQ, RabbitMQ, etc. A lot of the messaging standards that are present there. It is a super lightweight messaging protocol by comparison to those because it's designed for Internet of Things. So it's designed for low-powered embedded devices out in the field to basically transmit telemetry data so it can be used to build large-scale IoT applications. And when we mean large-scale, we're talking about millions of connected devices potentially. So you can imagine, for instance, a large power plant operator trying to gather meter data from millions of power meters connected to homes and commercial buildings in a specific geographic area. Or it might be for a really large manufacturing system that has lots of small devices that are all embedded and are controllable via MQTT inside a manufacturing line. What makes MQTT attractive for IoT is that it's a lightweight protocol, so it compresses to a very small size. It supports reliable deliveries. It has various qualities of service you can use to specify what level of effort should be used to try to deliver this message. And then on top of that, it's designed to work over unreliable networks. So for instance, if you're building power meters, you're probably not going to have a persistent Wi-Fi connection to go ahead and transmit data. Instead, what you usually have to do is transmit things over RF, radio frequency, which is much more lossy and low bandwidth by comparison. The fact is that because MQTT supports these very concise payloads, and it also supports the ability to work with brokers, you can go ahead and basically daisy chain these small MQTT packets until they reach a gateway, and then you can begin transmitting them up to like a broker controlled by the power plant that can actually start doing real things with those packets, like balancing the power grid or generating invoices for customers. This is from the MQTT.org website. This is sort of a general idea of like how the protocol is supposed to work. So you have, let's say, an MQTT client that functions as a publisher. This is usually a device embedded out in the field somewhere. Then you have an MQTT broker. This is going to be something like EMQX, or even RabbitMQ and NATs and other technologies all support being an MQTT broker potentially. And you have a number of different subscribers that can pull data from this broker and use the data published by devices to actually do real-world things. So in the case of a meter data management system, it's what a power plant or a public utility like a water company might use. You might use that to do things like generate invoices, or if you notice that a customer is exceeding way more water than they normally would at this time of day, maybe you'll send them an email or a push notification letting them know that you think they might have a water leak in their system somewhere. So those are some examples of like how MQTT gets used in the real world. So this is an example of the type of problem that we're asked to solve in the meter data management space. And now typically we hadn't worked directly with the MQTT layer itself. That's the protocol used to connect the gateways with the brokers and the consumers of the broker as well. That's sort of where MQTT fits into the picture. Normally with Akka.NET stuff that we do around here, that's usually details of how the consumers do their job with the MQTT data after they get it. So that's normally where we've worked with it. This is the first time we're asked to take a look at the MQTT layer on our own. So in this case, this is kind of what a standard meter data management problem might look like. Let's say you have 1 million homes that are all consuming power from an electric company, and each of them has a smart power meter that communicates over short frequency radio. So the bandwidth is limited. It doesn't have a direct internet connection. What the power company is typically going to do is install a number of gateways that aggregate data from, let's say, 5 or 6 homes. The number could be larger or smaller. It depends on a lot of factors like how close together the homes are, things like that. But that's more or less sort of the architecture that they're going to use to try to aggregate all this data and eventually stream it into their data center, where they're going to have an MQTT broker like EMQX in this instance. And then they're going to have a number of applications that pull those messages off of the broker. The brokers in this case, they're all going to be clustered under a load balancer for fault tolerance and scalability purposes. But the really interesting problem is the headroom and capacity planning that we have to do. One of the things that we're going to have to do is budget what happens if, let's say, at peak load, every single one of these gateways is reporting at least one reading from all their different aggregated homes there. So what happens if every single gateway publishes a message at the exact same time? Now, the system's designed not to do that. They stagger the gateways, so this shouldn't happen. But because we want to be responsible and make sure that this system operates even under peak strain, this is a headroom planning requirement that we have. So in order for this system to not lose data, even if we're running at a higher quality of service, we need to make sure that the consumers can quickly drain all of the messages that are being pushed to the broker. So that means that each one of these consumers needs to be able to process roughly 40,000 messages a second if we have 5 of them. So that's basically the set of constraints that we were given for this project that we were looking into. And we decided to take the proof of concept that this user gave us, which was built on top of MQTTnet, and take it out for a test drive. We took their reproduction sample and we tried to go ahead and measure the performance. This uses MQTTnet, which is the most popular standalone MQTT library in .NET currently. And what we observed was the fixed throughput between the stress tester application they gave us and the actual consumer they gave us would peak out at roughly this level of performance, about 12,000 messages per second. Some of that was because the client that they gave us was logging super heavily, which actually caused it to slow down when it was publishing. We were eventually able to improve the performance on this to have it push closer to like 100,000 messages per second. And that's after we also decreased the message size. The default message size they were using here is 8 kilobits, which is pretty big for an MQTT network. So the system here is basically sticking around 12,000 messages per second with one consumer and about 100 publishers all hitting the same broker all at once. So we're nowhere close to the number that we need to be. However, it gets worse. The longer the sample ran, the greater the number of connections, the stress tester applied to it. So we started to see eventually the client was struggling to keep up. Now, one thing I want to point out is that EMQX's default settings on queue length and basically how many messages can be in flight at any given time are ridiculously low. Something like only 32 messages can be in flight at any given time, and the number of messages stored in a topic which is basically it's a topic broker system. The number of messages stored in a topic defaults to 1,000. So this system would overshoot that in no time at all, and it would start disconnecting the client when that happens. So the first thing I did was reconfigure EMQX to have a much larger queue size, allow up to 60,000 messages to be in flight at any given time, and don't disconnect clients when we start having trouble keeping up, and don't drop the queue, basically. So I did a couple of settings changes to harden EMQX a bit. But what we saw was this sustained back pressure where basically MQTTnet struggled to keep up, and after a while would just gradually get slower and slower and slower. A lot of this could have been because of EMQX. Honestly, I've seen a lot of weird behavior from it. But we decided to go looking for answers out on the internet as to how well MQTTnet could perform if we did some optimizations to it. Maybe we changed some configuration settings around. So we went looking for a couple of answers. So, I had never worked with MQTTnet before, and so I decided to take a look at it and see if there's something I could do to try to improve my performance working with it. So I scrolled down to the README and I saw that it's performance optimized and should be able to achieve speeds of roughly 150,000 messages per second, which should be more than enough for my purposes. So I decided to go ahead and pull up that benchmark and try to run it locally. So I'm going to go ahead and grab the benchmark here. And I want to run the round trip processing benchmark. So I'm going to go ahead and turn the recording off here so it doesn't affect the benchmark. And we'll take a look at the numbers once that's done. Okay, so I've got my numbers here, and so we processed 100,000 messages received by the client in about 1.3 seconds is what the mean time was for that. So in terms of how I would compute that into a messages per second number, it's easy enough. Let's go and grab a calculator here. We'll go ahead and do basically 100,000, and we will go ahead and divide that by 1.311. And that's more like about half of the performance that the documentation said we'd get. This is 76,000 messages per second. Now, bear in mind, I'm running on a fairly high performance development machine here. So, but I'd expect to get in like a real virtualized environment with VMs will probably not be quite as high as that. So, okay, this made me a little suspicious. So it's like, okay, I'm only getting about half of the performance I promised, but this is still way higher than the number I was seeing pushing real payloads around. So let's go ahead and take a look at what this client was actually doing in its benchmarks. So this is the benchmark that we're running. It's running on .NET 6. And most of the work is being delegated to this class down here, handle 100,000 messages and receiving client. All right, let's take a look at this class. So it starts up a little test server. So it's basically using in-process TCP. That's the exact same thing we're going to end up using in TurboMqtt a little bit later. We create a little client, we connect to it, we wire up the event received, we use interlock.increment to go ahead and toggle up the number of messages we're receiving. That's all well and good. And then here's our loop where we're doing publishing down below here. Every 100 messages, we're going to create a task, and that task is going to publish, looks like 1,000 individual messages before we disconnect from the client here. So we have a test server, a test client that's doing receiving, and then we have, it looks like 100 test clients that are all doing publishing in order to try to get this to run as quickly as possible. One thing that you're going to notice here is that we have a topic and we're publishing that message, but what we don't have is a real payload. And that's kind of one of the things that I believe we need to add in order to try to get a more realistic measure of the performance that we're getting. So if I go ahead and pull up my little client here, I went ahead and I added a real payload, which is basically identical to the little JSON payload that we were using a bit earlier in the real test app that we had fired up. So we're going to use that going forward, and I'm going to append that payload to each one of these test messages. So let's go ahead and rerun the benchmark with a real payload associated with it and see how well that does. So by the way, one little detail I need to correct from earlier is that that message that we're testing with isn't actually 8 kilobits. It's about 1,100 bytes, so 1.1K. So it's a little bit lower than this. So we went ahead and reran our experiment using that 1.1 kilobit real payload, and now we're getting about half the performance of what we used to before. We're doing about 2.6 seconds on average to go ahead and clear out 100,000 messages. We're also allocating double the amount of memory we used to. No surprise there, since we're using real messages now. And yeah, our performance is about 38,000 messages per second here. This would actually be totally acceptable for us if we could actually achieve that inside our application. However, it's not what we were observing, probably because this is going over quality of service level 0. This is what you get when you don't have any reliable delivery turned on. As soon as you add a higher level of quality of service level, the number of round trips that need to happen between the publisher and between the subscriber, both talking to the broker, is going to increase. It's going to double the amount of message traffic that's going to have to go back and forth. So even with quality of service level 0, we would still have a little bit of trouble hitting our performance target. In order to do 200,000 messages a second spread out across 5 processes, you want to do about 40,000 messages a second. And you want some headroom beyond that even in order to account for things like garbage collection overhead. We're not able to cut the mustard here, even at a lower quality of service level. So we need to go back to the drawing board and see what our alternatives are for trying to find a way to hit our performance target. So that's when I decided to go to LinkedIn in search of answers. So naturally, as one does, if you're out there looking for professional advice, you take your query to LinkedIn or possibly Twitter. In this case, I took it to LinkedIn because I have a lot of people in my network who do a lot of low-level IoT stuff. And the advice they generally gave me was change out your entire platform for how you're doing MQTT. So get rid of EMQX, use NATs, use Kafka. I don't even know if Kafka supports MQTT. Use Rabbit, et cetera, et cetera. And while those suggestions are totally valid and fine in the context of things that may have worked for you, I'm not really in a position to turn around and tell a public utility company, hey, why don't you change out all of your IoT gateways and your, broker in order go ahead and replace those technologies entirely in the hope of trying to hit a higher performance number. I've got to come to them with evidence. And the issue, as far as I could tell, was not the broker and was not the gateways doing the publishing that were the problem. It was the rate at which we were able to clear messages off the broker. That was fundamentally what was at issue. So this feedback prompted me to go ahead and decide to look, okay, how hard could it be really to build my own MQTT client from scratch? So I decided to start diving into the details of the MQTT 3.1.1 protocol. That's a little bit simpler and has fewer fields to manage than MQTT 5. And MQTT 3.1.1 was perfectly fine for this use case that we were supporting. So I decided to dive into that. So after exhaustively trying to make MQTTnet hit our numbers, we decided that maybe it'd be best if we took a stab at writing our own MQTT client in C# to see if we could try to hit the performance target that was given to us. So before we wrote any code, I made the following design decisions early on. The first was that we were going to use system.memory for packet encoding and decoding. Now that's a pretty obvious choice. That's what everyone uses for buffer management today because that gives you the best opportunity for trying to do things like zero copy, buffer manipulation. But what's not obvious is implementing a packet size estimator when you're on the right side of the operation. MQTT is a duplex protocol. On the right side, you have the opportunity to take advantage of buffer pooling, where you go from having the message given to you by an end user to turning it into the buffer that's going to ultimately be written out to a socket somewhere. Well, what a packet size estimator will allow you to do is accurately predict how many bytes this fully encoded packet will occupy in a buffer. This makes it possible to pool many different outbound writes that all need to be delivered at the same time together into one contiguous buffer. This is going to make memory pooling work a lot better. It's going to reduce memory fragmentation because all of that memory will be accessed sequentially when it's being written out to the socket, and will generally improve I/O speeds pretty tremendously. One thing we couldn't really do is you can't really use buffer pooling on the read side in a system like this. And the reason why that is that because we're just handing over decoded packets to the end user, there's no telling when they're done with them, unless we try to implement some sort of reference counting scheme. And that is kind of fraught with a lot of different potential places it can go wrong in .NET, having done it once before with Akka.NET, actually. So we were not inclined to do that. We decided that, on the read side, we're just going to new up a buffer after we pull things out of the socket. And we're just going to deliver that to the end user. That way the garbage collector can figure out when they're done using it, and we're not going to run into any weird memory corruption issues or buffers getting freed earlier than they're supposed to. All the other sorts of things that can go wrong when you're trying to do fancy stuff with buffer pooling on the read side in an asynchronous system like this. We decided we were going to use Akka.Streams for I/O batching, both on the inbound and the outbound side. On the outbound side, this allows us to encode packets into groups. This I/O batching system that Akka.Streams is going to give us is going to work very well along with the packet size estimator, and it's going to make sure that while we're waiting for one pending write to finish to the socket, which is just a async value task that's kind of kicking off behind the scenes there, while that write is underway, we're already preparing the next write, and we're trying to gather as many packets as we can, and we're going to try to fit it into a maximum sized frame before it goes out over the wire. That's going to reduce the number of system calls, which is going to help keep our I/O throughput higher, and it's also going to keep our stability higher too. We're going to have consistently high throughput when we do this because we're not hitting the system calls as frequently on the socket layer when this is happening. So that's the outbound side of I/O batching. On the inbound side, we're going to model things as an event stream for the API that the end user is ultimately going to access. And we're going to do this using system.threading.channels. MQTTnet and the other libraries we had taken a look at in .NET all used event handlers for being able to process received events over MQTT. And I think that's a little outdated. We decided to go ahead and expose all the events as a stream. That would allow the end user to use things like async enumerable to process those, which gives us back pressure support. So when we're doing things like back pressuring, we can go ahead and pull a whole bunch of messages off the socket, and we can decode them, and we can automatically start doing things like, if we're configured to do so, automatically acknowledge them even before they arrive to the end user. That's going to help make sure that we're taking strain off of the broker, even if the actual end user code is busy doing something else. So that was part of our design from the get-go, is to leverage Akka.Streams in both of these places to make the I/O more efficient and to allow other asynchronous things to happen behind the scenes. We're going to use Akka.NET actors for handling all of the acknowledgments for quality of service 1 and 2. This sort of out-of-band asynchronous messaging is something that Akka.NET can do quite easily. So we have some actors on the publish side and on the receive side for being able to handle the higher qualities of service. If we're using quality of service 0, which is fire and forget messaging, we don't need to do anything. It's pretty easy. But if you have quality of service 1 and 2, we have to keep track of which packets have been published. We have to optionally, on the publish side, keep track of which packets need to be republished in the event that we haven't gotten acknowledgement back on time. And we also have to keep track of, if we're doing quality of service level 2, exactly once messaging. There's a whole nother layer of handshakes that goes into marking a packet as fully received. That's another thing that we're going to have to keep track of and potentially reissue acknowledgments for on the publish side in particular. So we're going to use some actors for that. We're going to use asynchronous enumeration for socket reads and writes. So we're going to await on a socket read. Once that read comes through, we're going to flush that data to a system.io.pipeline. And once that pipeline has reached enough buffer size to go ahead and do something, it'll flush that data into Akka.Streams. That Akka.Streams model is what we described a few bullet points above up here. That's going to cause that channel reader to, basically tick, and the user will receive a new event after it's gone through all the processing in our Akka.Streams pipeline. On the right side, we're going to have a channel reader that our transport's going to pull from, and there's going to be an async enumerable there. Every time we enumerate from an event that's pushed into the channel reader, we're going to try to flush that buffer. And then once that buffer has been flushed over the network, we're going to grab the next available buffer. And we're going to keep doing all of these things asynchronously. That way we're not blocking a real thread at all, and everything is leveraging asynchronous I/O and .NET very efficiently. Finally, we're going to take advantage of system.io.pipelines for TCP. So that's already implemented. We're going to take a look at that in one of the later parts of the series. But we're also going to try to implement the QUIC protocol. QUIC is basically the backbone of HTTP 3. It's a reliable streaming protocol implemented over UDP. It doesn't have some of the historical baggage that TCP has and isn't as susceptible to some performance problems such as head-of-line blocking. That's not implemented yet, so we might deal with that a little bit later on our YouTube channel. But that was part of the design requirements I came up with on day one. So to kind of show you where we've gotten with just TCP so far, at the moment, pushing those 1.1 kilobit messages over the wire at quality assurance level 1, so this is the QoS 1 we talked about, our system is able to handle about 66 to 70,000 messages a second over EMQX. And this is using some stress tester code that is part of the TurboMqtt project. So in part 2 of this series, we're going to go ahead and cover packet parsing with system.memory. We'll include the packet size estimator scheme that we talked about. We'll also go ahead and cover some of the benchmarks and some of the unit testing that we did to make sure that this all works. So we're going to go ahead and cover that in our next part of our series. Please go ahead and like and subscribe and stay tuned for part 2. Thank you very much.